In this video, I am going to define the comparison of topologies and closed set on a topology and solving the one theorem on topology. So, in this video today I am going to explain the definitions of comparison of topology and closed set and how to define the closed set on topology and theorems on topology. So comparison of topologies. Let definition. Let X be any non-empty set. X be any non-empty set. X be any non-empty set. Let T1 and T2, let T1 and T2 be topologies on X, if T1 is subset of T2. If T1 is subset of T2, then T1 and T2 are comparable. Here, T1 is smaller than T2. Okay. Let X be any non-empty set. Let T1 and T2 be topologies on X. If T1 is subset of T2, then T1 and T2 are comparable. Here T1 is smaller than T2. For example, here example can be considered as discrete and indiscrete topologies. Okay. Indiscrete topology means T can be defined as null set and X, and discrete topology can be considered as T2. That discrete topology is nothing but P of X. P of X means all the collection of members of all the collection of subsets of X. It means it is called as the power set. Power set can be denoted by P of X. So here we containing the elements as subsets of X. Here we have T1 is equal to pi null set and X. These two are the elements of T2, or this set is T1 is subset of T2 because already power set means empty set and X is existing T2. Therefore, this T1 is subset of T2. T1 is subset of T2 means T1 and T2 are comparable. Therefore, here we write T1 is subset of T2, that is T1 subset of T2. Therefore, T1 and T2 are comparable. The next definition is closed set. Closed set. Let X be any non-empty set. Let X be any non-empty set and T be topology on X and T be topology on X. Let X be any non-empty set and T be topology on X. Then subset of T is called as subset of T is called as open set and its complement is called as closed set. Let X be any non-empty set and T be topology on X, then subset of T is called as open set and its complement is called as the closed set. Example here, X can be defined as X is equal to ABCD and the next T is equal to empty set A, B, C, D. So A, B, C and here it is B, C, B, C, A, B, C, A, C, A, B, D, A, C, A, B, D, X. Okay. Example is X is non-empty set A, B, C, D and T is the null set A, B, C, B, C, A, B, C and A, C, A, B, D and element or member X. Here this T is topology on X or not. So for that we have consider first condition as empty set. This is belongs to T. It means it is satisfied. Second condition, X belongs to T. It is also satisfied. And the third condition is union of member of T is again a member of T. So A union B union C, that is ABC. B union C, that is BC. A union C, that is AC. And next A union B union C union ABD, then it is ABCD. It means third condition is also satisfied. The next fourth condition, finite intersection of members of TOE is again a member of TOE. So finite intersection means empty set intersection A, that is empty set only. A intersection B, that is also empty set, it is there in T. B intersection C, that is empty set, it is also there in set T. And similarly B intersection BC is nothing but element B or set B. This is also a member of T. Therefore all the fourth conditions are satisfied. Therefore this T is topology on X. If this T is topology on X, then each subset of T is called as open set. Here open set can be written as open sets. Open sets are here. These all members can be considered as open set, that can be written as empty set A, B, C, AB, BC, ABC, AC, ABD, X. These are the open set and now we write the closed set. Closed sets are complement of subsets. Complements of subset is called as the closed set. So complement of empty set is X and complement of A is BCD. Complement of B is ACD. Complement of C is ABD. Next BC. BC means complement of BC is nothing but AD. complement of ABC is nothing but D. Complement of AC is nothing but BD. Next, complement of ABD is nothing but C. Then complement of X is nothing but empty set. These all are the closed set. First, they are given the non-empty set and T. Here we have to check this T is topology on X or not. If it is topology on X, then we consider as open set as subsets of T. Subsets of T means all the members of T can be considered as open set, and each member's complement is called as the closed set. Here empty set complement X, complement of A is BCD, complement of B is ACD, complement of C is ABD, complement of BC is AD, complement of ABC is D, complement of AC is BD, and complement of ABD is C, and complement of X is empty set. This is the definition for closed set. Next we go to the theorem. Next we go for the theorem. Theorem is let X be a non-empty set let X be a non-empty set. Prove that intersection of two topologies on X is a topology on X. And give an example. To show that union of two topologies need not be topology on X. Okay, the theorem is let X be a non-empty set. Prove that intersection of two topologies and on X is a topology on X, and give one example to show that union of two topologies need not be a topology on X. It means here if we consider two different topologies, that is T1 and T2, intersection of T1 and T2 is also the topology on X. Here we have to show intersection of T1 and T2 is also topology on X. Therefore, we have to consider since proof. This is important for 5 marks. Proof. Let T1 and T2 be two topologies on X 2 topology on X. Then we have to prove that T1 intersection T2 is a topology on X. Okay, so let's start the first condition. First condition is empty set belongs to T1. T1 and T2 are topology on X, means empty set belongs to T1, and this empty set is also an element of T2. Therefore, empty set belongs to, and here also T1 also contains empty set, T2 also contains empty set. It means empty set is a common element. Therefore, we can write empty set belongs to T1 intersection T2. Then again second condition. Second condition is T1 and T2 are topologies. So X is an element of T1 and X is an element of T2. Okay. Then it means X is a common element in T1 and T2. It means X belongs to T1 intersection T2. Okay. Then next we write we have to check for union and intersection. If these two conditions are satisfied, then only we call T1 intersection T2 is topology on X. Therefore, here we consider again third one. Let G lambda belongs to T1 intersection T2. It means a set G1 is element of T1 intersection T2, then it is a common, G lambda is common element for T1 and T2. Therefore, we write particularly G lambda belongs to T1 and G lambda belongs to T2. It means union of G lambda belongs to T1 and union of G lambda belongs to T2. It means G lambda is indexed set, that is belongs to T1 intersection T2, and this particularly G index set is an element of T1 and index set is element of T2. Therefore, its union means it is union of G lambda belongs to T1 and union of G lambda belongs to T2. It means these two are the common elements in T1 and T2. Therefore, we write it as union of G lambda belongs to is an element of T1 intersection T2. Okay. Then next, for that fourth condition, finite intersection of two members of T is again a member of T. So for that, here we consider two sets. Let G and H are elements of T1 and T2. Sorry, T1 intersection T2. Then G and H belongs to T1 and G and H belongs to T2. G and H are the common elements in T1. It means G intersection H is an element of T1, and here also G intersection H is also an element of T2. Okay. Again here G intersection H is common element for T1 and T2. Therefore G intersection H is an element of T1 intersection T2. Okay. For finite intersection, we have considered two sets. G and H are elements of T1 intersection T2. G and H are the elements of T1. It means G intersection of G and H is always exist in T1. Similarly, G and H are elements of T2 or members of T2. Intersection of these two members is again existing the second topology exists in topology T2. Therefore, G intersection H is common element for both T1 and T2. Therefore, G intersection H belongs to the T1 intersection T2. Now, this T1 intersection T2 is topology on the given set. So, hence we complete the proof, that is, let X be non-empty set, then intersection of two topologies on X is topology on X. Therefore, we write here, hence T1 intersection T2 is topologies on X, is topologies on X. Therefore intersection of two topologies intersection of two topologies is always topology on X. Okay. But union of two topologies is union of two topologies is need not a topology. Okay, for that we have to consider the example. Example is, the next step will be, we have to show the union of two topologies need not be a topology on X. For that we have to consider example as X is equal to ABC, and T1 can be defined as empty set A, AB and X, and T2 be null set C, BC, X. Okay. Just say this T1 and T2 both are the topologies on X. Here we have to show that T1 union T2 is need not be a topology on X. If I can consider T1 and T2, T1 union T2, then it is first two elements. T1 union T2 means it is empty set X, A, AB, C, BC and X. Okay, here the element A union C, the members of T1 union T2, A union C is the AC, set AC, but this set AC does not belongs to T1 union T2. Here we consider set A union set C. First and second condition is satisfied because empty set and X both are an elements of T1 union T2. Okay. Then third condition is arbitrary union of members of T is again a member of T. It means I can consider set A and set C if these two sets union is AC, but that set AC does not belongs to T1 in union T2. Therefore, this is not a topology on X. Therefore, here we write T1 union T2 is not a topology on X because A union C is AC, but this does not belongs to T1 union T2. It means it is not a member of T1 union T2. Therefore, it is not a topology on X. Thank you.